Welcome back, everyone. Now that we've gone over a couple of theoretical concepts, let's go ahead and take a closer look to see how PyTorch actually implements gradient descent using its auto gradient function. Let's head over to the notebook and get started. Okay, here I am at an empty notebook where I've already imported Torch. One thing I want to point out is to definitely take a look at the PyTorch Gradients notebook that actually goes along with this lecture. So I'm referring to this PyTorch Gradients notebook. It's the first notebook in this subfolder for this section of the course. The reason I highly suggest you actually go through this notebook is a lot of what we're doing, we've actually written out for you in Markdown, in LaTeX, so you can actually see the formulas. We'll be implementing these formulas throughout the lecture here programmatically, but in case you want to see it written out neatly, you can also check out our notebook. And as you go further along, you can see here the various formulas that we've written out as far as showing how to calculate the derivative. Okay, so what we're going to do is we're just basically going to work out through this notebook, but I would highly encourage you to just take the time to actually just read through this notebook, because step by step along with the markdown is actually really helpful. Okay, so let's go back and actually implement the ideas of the auto gradient. So this is automatic differentiation. So again, in previous sections, that first section of the course where we're talking about PyTorch basics, we created tensors, performed a variety of operations on them, but so far we haven't done anything to store an actual sequence of operations or apply the derivative of a completed function. So let's go ahead and introduce the concept of the dynamic computational graph, which is comprised of all the tensor objects in the network. So now that we understand tensors, we can begin to understand this graph that is built from these tensors. So first, let's go ahead and show you how you can use a tensor object along with the auto gradient functionality of PyTorch. So what we're going to do here is I have a function, which is the same function that's in the notebook here. It's going to be y is equal to 2x to the power of 4 plus x cubed plus 3x squared plus 5x plus 1. And we're going to use PyTorch to actually calculate its derivative. Since calculating a derivative, as far as just one step backwards, that essentially is backpropagation. So let's go ahead and print the gradient of this function. So we'll come back here. We've imported Torch. Now let's go ahead and define x. So we're going to create a tensor. So we'll say x is equal to torch.tensor. And what we're going to do is we're going to provide just 2.0. But the key thing that we're going to do here is we'll say, and make sure we spell this right, requires underscore grad or grade for gradient is equal to true. So go ahead and run that. So this sets up computational tracking on the tensor. So now PyTorch can keep an eye on this tensor throughout the computational graph. It's not just floating around as a separate variable. So we have this tensor, and now let's go ahead and define a function. We'll say y is equal to, and here I'm just going to copy the function that we have in that notebook. So that's 2 times x to the power of 4 plus x to the power of 3 plus, and we'll say 3x to the power of 2 plus 5 times x plus 1. Essentially just a normal polynomial function. So if I take a look at print y, so here after printing we see the result is 63, which if you wanted to explore this on your own, you can see that if you scroll down in the notebook, if you just manually plug in 2 into that equation, you do get back out 63. And what's really interesting is since y was created as a result of an operation, so here's y and here's the operations we're performing on this tensor, where we're requiring a gradient and the tracking, then because we were doing that sort of tracking, there's actually an associated gradient function, and the gradient function is right here, grad for gradient underscore fn for function. So we have that now gradient function, and what we can do is we can actually say y dot, and if you hit tab, you'll see a bunch of methods come off of this object. And in fact, let's go ahead and explore the type of y. Notice that it itself is a tensor, but interestingly, what we can do is say y dot backward, and this is going to perform back propagation. So let's go ahead and then display the resulting gradient off of x. So now take x and call the gradient, which is just grad, you don't call full gradient, and we get back the result of 93 stored within this tensor object. So what does 93 actually represent? 93 is the representation of if you were to plug in the x value into the first derivative of y with respect to x. So that's kind of a complicated way of really just saying, if you take a look again at our lecture notebook, essentially what we've done is when you perform y dot backward, essentially that single derivative with respect to x, that first back propagation, then recall we have this derivative right here. So I'm going to zoom in just a little bit so you can see this a little better. We have the function, and then we have the derivative. So we can see here, this is the derivative of that function. And if you were to pass in our current x value, which we defined as 2, into that derivative, which we actually show you the full steps right here, then you get back 93. So 93, that's going to be the slope of the polynomial at that point where x is equal to 2. So we have x equal to 2, and recall when you plug in x equal to 2, the result of y is 63, which means the derivative value at 2 is equal to x, and then y is equal to 63 is 93, which after we perform that back propagation, we can get back off of x dot grad. And then you could kind of switch around the x values beforehand to see the gradients if you were to plug in different values of x. So that's why we call the gradient directly off x and not off y, because it is dependent on what the value of x is. Essentially, answering the question is, if you were to plug in some value of x into the first derivative of y, what would be your resulting value? And in this case, it's 93. Okay, so that's what we just did. Essentially just a single run through back propagation, just one step, and it's just the first derivative with respect to x. Now what we're going to do is we're going to perform back propagation on multiple steps. So we're going to do something a little more complex, and we're going to involve layers y and z between x and our output layer out. So let's go ahead and take a slight look at this and what it's going to look like. What we're going to do here is we're first going to create a tensor. So let me create a couple cleared cells there. We'll say x is equal to torch.tensor, and this will be two-dimensional, so note my use of brackets here. On the first one, we'll say 1, 2, and 3, and I'm making these floats, and then in that second layer we're going to say, or that second row, 3, 2, 1. And to make sure everything's linked, I will say requires gradient is equal to true. Let's go ahead and print x, see what it looks like. So I can see here I have 1, 2, 3 in that first row, and then 3, 2, 1, and it requires that gradient. Keep in mind, depending on what YouTube videos you're looking at or what presentations you're looking at, some people just say grad or grade. So you may hear some people pronounce things with G-R-A-D as grad. You hear other people pronounce them as grade for gradient. Either is okay. Don't worry too much about that. Okay, so let's go ahead and create the first layer with y is equal to 3x plus 2. So I'm going to say y is equal to 3 times x plus 2. Recall that x is equal to this tensor, and again I'm saying multiply it by 3 and then add 2 to it. So if I print out y, I can see the result of all that. So let's just take a look at this one. So 3 times 1 is 3, plus 2 is 5. And we have it over here as well, so it makes sense that we have 5 on this first one and 5 on this last one. So that's our first equation. Let's go ahead and make another equation with z. So we're creating kind of a second layer here. We'll say z is equal to 2 times y. And let's go ahead and say squared. So we'll say z is equal to 2 times y squared. And then if I go ahead and print out z, let's go ahead and take a look at the simplest one, which is 50. So what I'm saying is take 5, square it, which is 25, and then 25 times 2 is going to be 50. So again, I have this series of equations that's linked to each other. I have my original values of x, then this formula for y, which uses those x values, and then this formula for z, which uses those y values. So note z is connected to y, then y is connected to x, and we're kind of building out this relationship. Now, what we want to do is let's go ahead and set the output to be the matrix mean. So we'll have this kind of final layer, we'll say out is equal to z mean, or the average value. And then we'll print that output, which is then reported back as 140. And note back again, we get this gradient function. So now what we're going to do is we're going to perform back propagation to find the gradient of x with respect to this output layer. So to do that, we simply need to say out dot backward, and then we'll go ahead and say print x.gradient, or x.grad. And we can see the results here, 10, 16, 22, 22, 16, 10. So this is the 2 by 3 matrix. And if we call the final out tensor, so if we call this final out tensor O, then we can calculate the partial derivative of O with respect to x of I in the following manner. And I'm going to bring back our lecture notebook because we've actually written out the math here for you, which uses the chain rule. And this is something we've already kind of discussed with backpropagation, but here you can essentially see the math that we just worked out ourselves for this connected layers of z with y with x and then that final output layer. So this was the result we just got. And what we're going to do is we're going to call this output layer, for notation purposes, just O. We can see here that we're going to calculate the partial derivative of O with respect to x of I. And then we're going to be using the chain rule. And then if you follow this along, so again, here's the chain rule that we kind of already covered. And then therefore, if you keep just calculating and pushing out this math, you end up getting the results where x equal to 1, x equal to 2, and x equal to 3, 10, 16, and 22, which are the results we got back here. 10, 16, 22, and then since it was reversed, 3, 2, 1, we got 22, 16, 10. So take the time to kind of look and see that if you were to do this by hand, the mathematics lines up with what we just did computationally. And lucky for us, we're just going to be not needing to calculate all these back propagations by hand. Instead, we'll just let PyTorch do it for us. Okay. Now, the last thing I want to mention is, as far as turning off tracking, there may be times when we don't want or need to track computational history. And to do that, as you may have guessed, you simply just say requires gradient attribute, and you just say it as false instead of true, which is what we've been doing. Okay, there is a less used method, which is called .detach, which can kind of detach it from the graph object. But really, if we ever need to turn off tracking, what we're going to do is we're going to say it requires gradient and then set that equal to false as needed. Okay. So go ahead and review these calculations. Make sure that these handwritten calculations or these kind of manually done ones match up with your expectations with what we just did computationally. Okay, thanks, and we'll see you at the next lecture.